Hello everyone, I'm Zhaleh Manbari. I want to present the paper entitled Parallel Local Feature Selection and High Dimensional Data Classification. In this presentation, first the roadmap is shown. Then we review feature selection literature, its challenge and its solution. In the following, the proposed method and its results are presented, and finally conclusion and a brief direction to future work is explained. As you know, technology is advancing rapidly. This advancement has led to the expansion of massive data. This data suffers from curse of dimensionality. Therefore, feature selection is a suitable solution to overcome data with high dimensions. On the other hand, with the growth of technology and the expansion of the colossal and varied data, concept drift emerges. This means that at any time or any part of the data, concept can be different. Therefore, local processing can handle this concept. Based on this roadmap, we are addressing local feature selection and providing a framework for it to handle this challenge. In this chart, classification of feature selection algorithms based on various criteria can be seen. According to the search strategy, this algorithm can be divided into complete, heuristic, and randomized methods. Feature selection algorithm based on relationship with learning algorithm are belonged to four main categories: filter, wrapper, embedded, and hybrid methods. And based on class label and its accessibility, this divided into supervised, unsupervised, and semi-supervised. An existing major challenge is that most of the feature selection methods intend to select a global feature subset that is applied over all the sample space. Therefore, an important point is that in some cases, in various regions of the input's sample space, different subset of features may be instructive. There is this challenge in all global feature selection methods, which we want to address. As you can see on the screen in this figure, the importance of local feature selection has been illustrated. In this figure, the samples with 3 features in 4 classes are shown in different markers. In A, by selecting subset features X and Y, the classes rhombus and circle are separable. But the classes multiplication sign and rectangle are inseparable. On the other hand, in B, by selecting features Y and Z, the classes multiplication sign and rectangle are separable, but the classes rhombus and circle are inseparable. And finally, in C, by selecting subset features X and Z, there is no identifiable class. But by local feature selection for each locality A and B, all 4 classes are classified clearly. The literature of local feature selection is limited and has been employed for special applications. These methods have not been evaluated on high-dimensional data, and the complexity of these methods on high-dimensional data is high. In maximality of literature, feature selection is wrapper or localization is performed for each sample, which in both of them they are unsuitable in confronting with high-dimensional and big data. Overall, the main drawback of these algorithms, besides ignoring the local behavior of the sample, is that they consider features independently, leading to a suboptimal subset of features. The proposed methods, as referred to PLFS, consist of 3 steps. Step 1, localizing input space. Step 2, selecting features in each region and training learner. Step 3, classifying test samples by dynamic integration of classifiers. We apply a technique for dynamic integration of classifiers. It allows us to determine what classifier and with what feature subset should be applied for each new instance. To local feature selection, we first need to identify the localities which may affect the local feature selection. For this purpose, we use a simple clustering method such as k-means. We claim the proposed method achieves an excellent result using the simplest approach. We know that it makes sense that the number of features of each cluster should be different, not a fixed number, because the number of instances of each cluster is different. But we have considered a fixed number just for simplicity. We are also aware about the fact that the number of clusters is an important issue and the type of clustering is not ineffective. But we wanted to prove the effect of local feature selection with the simplest parameters. Definitely, with smart selection of all these parameters, the result will be great. And this will be our future plan. In the first step, input space divides into several localities by k-means. Since concept drift usually occurs across classes, in the proposed method, the number of clusters is considered to be a multiple of the number of classes. After representing the problem space into several regions or clusters, a global feature selection method is performed. Note that this step is performed in parallel. At the end of this step, for each area, a subset of the related features is selected. Then, the reduced dataset of each cluster is used to train its learner or classification. Therefore, according to the number of clusters, we have classifiers trained. Note that we apply the same basic idea that each classifier is most reliable inside a particular sub-area of the instance space. An important issue in this procedure is classifying the test samples. Which classifier should be selected for the classification of the test samples? In global feature selection methods, the classification is done only by the existence classifier, but there are several classifiers in the proposed local feature selection process. Therefore, the integration of classifiers is essential. We use the weighted nearest neighbor classification, WNN. The use of WNN conforms to the assumption that each base classifier is most reliable inside certain sub-areas of the instance space. This assumption is also supported by the experiences that classifiers usually work well not only in certain points of the space, but also in sub-areas around the points. There are two variations of the application phase. One, dynamic selection or DS, and two, dynamic voting or DV. In DS, a nearest classifier is selected to produce the final classification. In DV, a weight is given to each base classifier, and each classifier gives its weight. A classification with the highest vote is then selected. You can see in the first formulation here, we have to choose this classifier with the highest weight. This classifier weights are equal to the inverse of the sum of the distance of X to its neighbors. Note that this distance is calculated according to the specific and limited features of each location. That means Euclidean distance from its nearest neighbors is calculated by just NF features, not all features, and it greatly reduces this complexity. The complexity of the proposed method is O proposed method is equal to O step 1 plus O step 2 O plus O step 3 equal to O n multiplied D plus D multiplied by log D plus n. For high dimensional data, this value is O n power 2. And when we utilize other improved clustering methods, this complexity may be reduced to O n log n. Note that our reported complexity includes the whole process of feature selection, from pre-processing to the classification of the test data, while often the reported complexity by other algorithms only belongs to the feature selection stage. Taking that into serious consideration, there appears to be a lack of fair comparison in terms of complexity. To have a fair and also comprehensive assessment, we have used different data sets, including 4 microarray data sets: colon, lung cancer, prostate, and SRBCT; 4 text mining data sets: alt, structure, function, and disease; and 2 other data sets, namely Madelon and Arsen, with NIPS 2003 challenge. To evaluate the performance of the proposed local feature selection method, the classification error rates (CER) are estimated in 3 experiments over SVM, naive-Bayes, and decision tree classifiers. The proposed method is compared with 2 state-of-the-art global feature selection algorithms called FSC-BUS, a hybrid filter-based feature selection algorithm that uses improved binary and system and clustering, and 2 PGVNS, high-dimensional feature selection via feature grouping. As shown in these figures, the local feature selection algorithm on the challenging dataset depicts its superiority. It clearly demonstrates that salient and efficient features are different in each area, and selecting a subset of features for the entire dataset reduces the accuracy of the classifier. For example, you can see on the screen for Arsen dataset, the performance of the proposed PLFS for SVM classifier is 20. And you can see there is a big gap between the proposed method with other 2 algorithms. This value, the CER for FSC-BUS is about 25, and for PGVNS on SVM classifier is about 37. Considering these figures on text mining datasets, it can be observed that the proposed method is still in the first rank. For example, here for alt dataset, you can see the proposed method on SVM and naive-Bayes classifier is by far achieved excellent performance. And for the structure and function, also this is the case. Finally, the proposed method is evaluated on microdataset, which is expected to have a noticeable effect in this type of dataset. According to this figure, the presented local feature selection algorithm in all datasets over all classifiers is extremely accurate. For example, the CER of the proposed method on colon dataset on SVM is around 11, which is significant compared to the global feature selection methods. And to the best of authors' knowledge, this accuracy has not been shown in any other algorithms. Finally, a clear summary of the performance of our method has been illustrated in these figures. You can see the overall performance of the proposed algorithm on all datasets. At a glance on SVM, you can see the proposed method is better in comparison with the other methods. This is the case for decision tree classifier and also naive-Bayes classifier. In the last section of my presentation, I'm going to provide a summary of the work and its objective, and also the future plan. Well, feature selection effectively reduces the feature space and thus the complexity of classifiers. Though several algorithms have been proposed, no single one outperforms all the other in all scenarios, and the problem is still an actively researched field. In feature selection algorithms, the goal is to select one optimal subset of the primary features. That may not always be useful, as drift often occurs in large datasets. Therefore, we propose a special feature selection algorithm to cover this challenge. Note that the proposed method improves any global feature selection methods. In fact, the proposed PLFS is a new framework that can be improved by future researchers to work on instead of improving global feature selection ones. For future work, this method has the potential to be bettered in several ways. For example, the number of clusters, which has been considered proportional to the number of clusters, may not be the best choice. A smarter methodology can be developed to integrate the number of clusters into the feature selection algorithm. Moreover, the number of attributes for each region can be selected by a more intelligent technique. Finally, as a future direction, we have a strong inclination towards meta-learning or learning to learn, and meta-classification, including the application of meta-learning in the classing section, few-shot learning in the feature selections section, and meta-classification in the classifier integration section. And last but not least, not free lunch. Many thanks for giving us the opportunity to present our paper in ICCKE 2021.